the most powerful AI systems ever built. The ones that can generate images from text, hold conversations, diagnose diseases from scans, and beat the world's best players at any game you name. They all share the same fundamental architecture. It's called a neural network. And the reason it has that name is that the scientists who invented it were trying to build something that worked like the human brain. They didn't fully succeed in copying the brain, but what they did build turned out to be extraordinarily powerful. Let's break down how it actually works. Your brain contains roughly 86 billion neurons. Each neuron is a cell that receives signals from other neurons, processes them, and either fires a signal forward or stays quiet. Neurons are connected to each other in vast webs, and the strength of each connection, how easily a signal passes through it, changes over time as you learn. That changing connection strength is how memory and learning work in a biological brain. An artificial neural network takes that basic concept and simplifies it dramatically. Instead of biological cells, you have mathematical functions. Each artificial neuron receives some numbers as input, multiplies each input by a weight, a number representing how important that input is, adds them all together, and passes the result through an activation function that determines whether the neuron fires strongly, weakly, or not at all. Individual artificial neurons are simple. The power comes from connecting huge numbers of them together in layers. A typical neural network has three kinds of layers. The input layer is where data enters. If you're building an image classifier, the input layer might receive the brightness values of every pixel in an image. If you're processing text, the input might be a numerical representation of each word. The input layer doesn't do any computation, it just passes data in. The output layer is where the result comes out. For a classifier that recognizes 10 different types of objects, the output layer has 10 neurons. The neuron that fires most strongly corresponds to the predicted category. If the cat neuron fires strongest, the network thinks it's looking at a cat. Between the input and output are the hidden layers. This is where the actual computation happens, and this is what makes neural networks powerful. Early networks had one or two hidden layers. Modern deep learning networks have dozens or hundreds. The word deep in deep learning literally refers to networks with many layers. Here's the intuition for why layers matter. The first layer of a network trained on images might learn to detect simple features, edges, colors, corners. The next layer combines those simple features into more complex patterns like eyes or wheels or the curve of a mouth. The next layer combines those patterns into parts of objects. The final layers combine parts into whole categories. By the time you get to the output, the network has built up a rich hierarchical understanding of what's in the image. Not because anyone programmed it to, but because that's what emerged from training. Training is how a neural network learns. At the start of training, all the weights in the network are set to small random values. The network is essentially making random guesses. You feed it a labeled example, say an image of a dog with the label dog, and it produces some output. That output is almost certainly wrong at first. You calculate how wrong it was using a function called the loss function. Then you use an algorithm called backpropagation to figure out which weights contributed most to the error. And you adjust those weights slightly in the direction that would have made the prediction less wrong. Repeat this process millions of times across millions of examples, and the weights gradually converge to values that let the network make accurate predictions. The computational cost of this process is enormous. Training a large modern neural network can require specialized hardware running continuously for weeks and cost millions of dollars in electricity alone. But you only have to train it once. After training, using the network to make predictions, called inference, is much cheaper and fast. Different types of neural networks are designed for different tasks. Convolutional neural networks are specialized for images. They apply filters that scan across an image and are particularly good at detecting spatial patterns. Recurrent neural networks were designed for sequences, like text or audio, where what came before matters for understanding what comes next. Transformers, the architecture behind ChatGPT and most modern language models, use a mechanism called attention to figure out which parts of a sequence are most relevant to understanding each other part. That's how they handle very long documents or conversations without losing track of what was said earlier. What neural networks can't do is also worth knowing. They're not infallible. They can fail in bizarre ways on inputs that look very different from their training data. They can be fooled by carefully crafted inputs designed to confuse them. They don't explain themselves. You can look at the input and the output, but understanding why a deep network made a specific decision is an open research problem, and they require enormous amounts of data to train well. Despite those limitations, neural networks have proven to be the most flexible and powerful machine learning tool ever discovered, and we're still finding new applications for them every year. If this helped you understand neural networks, subscribe. We break down AI every week in plain English.